All right, so welcome to module number 19. So far, we've had several modules on scientific programming, and the big point in this segment of material was that as we're moving to larger data sets, when looking into data science problems, with these larger data sets, they allow us to process more information, which in many cases allows us to perform the learning procedure better, which allows us to act on that information, act on the conclusions from that learning, providing more, call it utility, profitability, however you want to measure it. But the downside is that to process a lot of data, you need to start getting the details right, because if you have an inefficient algorithm, forget about it. It's going to be horrendously slow. It's not going to take hours, it's going to take decades, okay? So that was a main point in this segment of the material. And we also talked about data structures. You need some familiarity with data structures. And of course, at a later time when you're working on something, you can read more about this, but you need some basic familiarity as building blocks to know how to put together reasonable algorithms. But now the last module of this segment of material, module number 19, is going to be about profiling. And profiling lets you write, not just write efficient code, but evaluate its efficiency and try to look for hotspots. So imagine that we have this assignment that we're going to develop a merge sort routine, and we're not going to do this. I'm just pointing out that the code is already on the course webpage, both in Matlab and Python. And our main structure is as follows. We have the merge sort routine where the input is X and the output is Y. I'm using pseudocode here. If X is short, I'm just writing as short, then well, if it's of length 1, then the output is equal to X itself. Or maybe it's of length 2, then we output the minimum of X followed by the maximum of X. Else, meaning X is not short, we look at the first half, Y1. We look at the second half, Y2. In the first half, we perform a recursive call to perform merge sort on the first half of the data. And Y2 will be similarly, a recursive call to perform merge sort on the second half of the data. And finally, we're going to call the merge routine to merge between the two halves in Y1 and Y2. So again, pseudocode, this is not real code. But how do we implement the merge? So we have two input vectors, X1 and X2. Presumably their links are either identical or very similar. And we're going to loop over the following procedure. We're going to, at every point of time, we're going to compare the first numbers in both vectors, and the vectors are being modified. Remember my analogy, two decks of cards, and you're looking at the deck at the top of each card, and these decks are already sorted, so the card at the top of each of the decks is going to be the smallest number, and then you're asking which is smaller. The smaller one, you're putting it aside and moving to our group, so we're moving the smaller card into our output array, and then we're incrementing the pointer in the deck of cards that we removed that card from. So we need to be able to deal with some details, such as whether the lengths of X1 and X2 are the same, but these are details and this can be done. And again, if the details are not identical, if the links are not identical, we can handle that. As long as the merge sort operates in such a way that the two merges, the two parts that we're merging are somewhat balanced, things will be n-log n in general. So now we get to profiling. You guys can go look at the Matlab or the Python implementation on the course webpage, but we want to verify that it works well. So that's when profiling comes in. Wikipedia describes profiling as follows. In software engineering, profiling, also called program profiling, software profiling, is a form of dynamic program analysis that measures, for example, the space, memory, or time complexity of a program, the usage of particular instructions, or the frequency and duration of function calls. Most commonly, profiling information serves to aid program optimization. So program optimization meaning that we want to improve our code. So profiling measures from our perspective, it'll be primarily the running time, which is consumed on each line or by each function call. And additionally, the number of times that each line or function ran. And here's a mini example. how to run profiling in Matlab, and similarly in Python, you can do similar things. X will be some random set of inputs. We turn on the profile with a profile on command. Then we run our merge sort routine, y equals merge sort of X. And then prof report, the profiler report, generates a detailed report of how the merge sort runs. The typical report, note that things are colored here, and we have different components. In the red, we have the running time. That's going to be the leftmost set of columns. Then we have in blue the number of times that the lines are called. Note how lines 2, 3, 4, 5, 6, and 7, or rather 2, 3, 5, and 6, 4 is commented out. They're called 59,048 times each. So presumably some routine was called roughly 59,000 times. And then we have a loop for n equals 1 to the sum of n1 plus n2. Presumably these are the links of the inputs of the merge routine. And then if x1 of index 1, so some condition. And this ran not about 59,000 times, but about 860,000 times. So basically, perhaps 15 times on average for each time that we're accessing the merge routine. And if the condition holds, we perform the commands, and that happens roughly 420,000 times, so maybe half of the 860,000. And then we perform lines 8, 9, 10, and if not, we don't. So we see the running time of lines 2, 3, 5, and 6 was less than 100th of a second each. And because line 7 ran 860,000 times, it took 5/100ths of a second. And this line number 8, where y of n gets x1 at location index 1, that runs fewer times, 400-something thousand instead of 800-something thousand, but it takes 18/100ths of a second. So apparently that line is a bit heavier for whatever reason. But the bottom line is that this information now allows us to identify hotspots in our code. So what you're going to do, you're going to look through all the lines with substantial running time, and you're going to make sure that you know why each of those substantial running time lines indeed took plenty of time, and you'll redesign as needed. So let me informally tell you the way how I often approach this, okay? So my approach is often as follows. Search for lines that ran at least, let's say, 10% of the runtime, okay? And for each of these lines, look at it, try to understand whether it makes sense, and can I explain why it's slow? So recall that at the beginning of this segment of material, recall that we had the example where x was the current, x was a list, and we're adding to x the number n within a for loop over n, and this was way slow. It took quadratic runtime, quadratic in n, whereas we expected linear in n, and that's because each time that we did that, the amount, this command that looks simple, it actually took linear runtime in n, whereas we expected it would be a constant amount of runtime. So we can, if we have inefficient lines in our program, we'll often realize that they take 20, 30% of the runtime, and we have a line of code that appears to be simple, and we don't understand why it's slow. And when we dig in and start thinking about it, we often identify that this, I wouldn't necessarily call it a mistake, but let's say a detail that we weren't paying attention to is often there. And once we catch it, the runtime often improves. So sometimes I've identified single lines that are 70, 80% of the runtime because of, again, some minor detail that wasn't considered in advance. And when you modify the code to keep this detail in mind, oftentimes that 70% becomes like 0.1%. So like complete collapse in runtime. And then you start focusing on the rest of the lines of code. So basically, you improve these lines of code if needed. And then you rerun, but now often you'll have, instead of, let's say, looking at lines that took 10%, you'll look at lines that took 5%. So you'll be a bit more detail-oriented. So initially, there are often lines that may take 20, 30% of the runtime, and those are lines that where maybe you have a good feeling what's going on there, and you know that you did what you could. But maybe there's a detail that can be improved. And after you take care of the really heaviest lines, then in the second pass, you might be willing to look at these finer details. So that's it. That's module number 19. That concludes the scientific programming material. And the following modules will start talking about optimization.